the linear algebra classes. We have, let me see, number one, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have more than 6 classes. Okay, so 1, 2, 3, 4, 5, 6. Okay, and for physics, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so anyway, we hope sorry, we can finish linear algebra and physics 1 at here. Okay, latest by 2, 3, 4, 5, 6. Okay, 6 of sorry, 6 of February. Of course, we have some backup class here. Okay, 4. Okay, 11, 12. Okay, yes, that's enough. So if you are going to book a flight tickets, okay, so you can do yeah, after the 6th of February, okay, 2026. Okay. And remember, we have final exams of linear algebra and physics 1, okay, after Lunar New Year's, okay, 2, 3, 4 of March, and 5th, okay, 2, 3, 4, 5, 6, and 6 of March, okay. Yeah. Anyway, we study lecture 2, okay, lecture 2 of linear algebra, and we hope we can finish lecture 2 in this afternoon, and then if we have more time, we go to lecture 3. Okay, yeah, so anyway, on Monday we discuss about how to calculate the determinant, okay, according to minors and cofactors, right? Okay, so you should remember that if we would like to calculate determinant, theoretically we need to calculate minors and cofactors. Yeah, Mij, and then you can so which of the determinants below is easier to evaluate? Of course, B. Why? Because you can recognize here is more zero element, right? So if we would like to get determinant of B, very easy, okay? You select this one, so you have minus 1, this is A, this is for 1, right? B for 1, for 2, for 3, and for 4. It does mean to the power of A, yeah? And then we have M for 4, right? M for 4. So that means you can get M for 4. And here, oh, I forgot we should have a minus 1 here because this is a B for 4, okay? So B for 4 is minus 1, so you get a minus here, right? And then this is C for 4, right? So minus 1 to the power of A, you get 1, okay? So minus 4. So you can delete this one and this one. So we can have minus 1, 0, 0, minus 2, 2, 0, 3, minus 9, minus 3. Okay? Yes, it's minus, right? And then we can select this one. Okay, so this one is, for example, this is C. So C11, C12, sorry, C31, C32, and then C33. Okay, so you get minus 3. Okay, and we times C33 and C33 is M33. Okay, M33 because equal minus 1 to the power of 6 is 1. So minus and minus, you get 3. M33, we delete this one and we delete this one. So you get times 2. Okay, times 2. So you get determinant is 6. Okay, determinant is 6. Here, determinant is 6. So you try to do the exercise how to calculate the determinants, and then you will be familiar with this. Okay, so if we calculate determinants of A, you take more times because we cannot recognize any zero element of this matrix. Okay, so we think about, we use elementary operations, okay, to modify A to become B. So if you can modify A to become B, you can get determinants very quickly. Okay, so now notice that determinants of A is 6, determinants of B is also 6. But if we calculate determinants of B, you can solve more times. Okay, yeah. So we think about, we apply elementary row operation to simplify A to become B. Okay, yeah. So we use elementary row operation. Okay. So now we have the theorems. Of course, for theorem, we need to demonstrate, but now we don't have more time. So we just accept the theorem. So let A and B, B is square matrices. You know, if we want to calculate determinants, A and B must be squares matrices. Okay. So when B is obtained from A by interchange two rows, we conclude that determinant of B is minus determinant B of A. Okay, yeah. So if we have A, we get B by interchange. So we conclude that determinant of A is minus determinant of B. Okay, like this. Or we can say determinant of B is minus determinant of A. That's okay. Okay. Yeah. So if we have A, we get B by scalar multiplications. Okay. Sorry, no. By the third rule, C times Ri plus Rj relate to Rj. So we conclude that determinant of A is determinant of B. Okay. And now if we have A, we would like to get a B. And then we use multiplication, scalar multiplication. CRI relate to RI. So we say determinant of A, E 1 over C, determinant of B. Or we can say, according to this one, so if you move C to here, you can get 1 over C determinant of B, E determinant of I. Okay, the same, But why I mention this one? Because normally we get B from A, you get B from A, so normally we determinant of is blah, blah, blah. Okay, so it's up to you. It's up to you. Yeah, you can remember this one, or you remember this suggestion. Okay. Yes. Okay. So now we have example. Okay. So we have A, you get B. We do what? We interchange, right? We interchange. We interchange R1 and R2. So we have determinant of A is minus determinant of B. Okay, so determinant of B is minus 11. So minus 11, you get determinant of A. So determinant of A is 11. Why? Because our purpose to determine to calculate determinant of A, not B. Okay, so that is the reason we need to follow the determinant is minus determinant of B. Determinant B is minus 11. So minus you get 11. Okay, so now A to B, we do what? Oh, multiplication, right? Multiplication. Oh, sorry. We SC with RI plus RJ relate to RJ. So we have determinant of A, determinant of B. And then equal to what? 2. Okay. And number 3, A to B. Okay, scalar multiplication RIC times RI relate to RJ. So you get determinant of A, E1 over C, determinant of B. And determinant of B is 1. And C is 1 over 2. So 1 over 2 is 2. 2 times 1, you get 2. Okay? Sorry. Okay. So now we consider a square matrix with 3 rows and 3 columns. Okay. So over here we have A. Okay. Yeah. And then we interchange. So if I interchange, I get what? We interchange R1 and R2. So we can get BE 1, 2, minus 2, 0, minus 7, 14, and 0, 3, minus 8. So if we make the interchange, we have determinant of A is minus determinant of B. Okay, so this one is B, right? This one is B. So when we calculate determinant, you just add minus here, you can get determinant of A. So that is the reason we have minus here. Okay, yeah. Continue. We factors minus 7. Okay, out of the second rows. Okay, we just take minus 7 out. So when we take the minus 7 out, okay, minus 7. So minus 7 and minus, you get sorry, or you just what is it? This one lie you times 1 over 7, right? With R2 relate to R2. So if we apply this one, so you remember determinant of IE is what? E 1 over C, and now C is 1 over 7. Okay, so that means 1 over 7 determinant of B. So that means 7 determinant of B. Okay, so if here we time 1 over 7 with R2, 1 over 7 with R2, so forget the determinant, you need to time 7. Okay, so you time 7. You times 7. So if you have minus, so here you get minus and minus and minus. Here you can get positive. Okay, so we only have 7. Okay, and here you get 0, 1, minus 2, because 14 over minus 7, you get minus 2. Okay, so here. That's what. Okay, now look here. We would like to delete this one is 0. So that means I times minus 3 with I2 plus I3 relate to I3. So if we do this one, determinant of A, E, determinant of B. Okay, so we keep 7. Okay, we keep 7 from here. Yeah, and here you can get the 0, right? Here you times minus 3 and minus 2 is 6. 6 minus I, you get minus 2. Okay, so now you get this one very easy, you know, very easy to get a determinant, right? So for this one, I choose, it's up to you. For example, I choose this columns. I choose this column. I can get 7 times 1, right? Times C11, right? C11. For example, here is C11. C11, that means we can get M11 because 1 plus 1 is 2, minus 1 to the power of 2 is 1. Okay, so you can get 7 times minus 2 minus 0. Okay, so you get minus 14. So determinant of IE minus 14. Okay, yeah. Yeah, you get minus 14. Okay. Yeah. Any questions so far? Okay, what are the questions? Wait. So basically, you just need to multiply the diagonals of the matrix, right? Yes, of course, you can do that. We have many ways. Okay, it's up to you. You are correct. Okay, I think this may be a lucky case where the matrix is already row reduced. Yes. Okay. Yeah. Okay. Yeah. We hope for the final exams, yeah, we get yeah the same case like this. Okay. Yeah. God bless you. Okay. Okay. Other questions? Yeah. Okay. Yeah. Please just type the questions. Okay. Yeah, it's up to you. You can apply the properties of triangular matrices. Okay, upper triangular matrices or lower triangular matrices. You can get the results also. Okay, yeah. Okay, so now we continue and then we will come back for the questions. Please don't be shy. If you have any question, just type the questions and then I will answer to you. Okay. Now continue. So if you don't like to use elementary row operations, you can use elementary column. That's okay. Okay, the same. Yeah. So it's up to you. If you are familiar with row operation, just use them. Otherwise, you can use elementary column operations. Okay. So yeah, example. Look at the examples. So here we use we use elementary column operations. Okay. So okay, so we can interchange C1 and C2. This is C1, this is C2, this is C3. Okay, remember when we interchange, we have determinant of A is minus determinant of B. Okay, so here, that's the reason here, when we interchange C1 and C2, we have the minus here. Okay, and then look at this ones. Okay, yeah, look at this one. Yeah, we can modify here to become 0 and 0 and 0. I mean, we get the diagonal element. We get the diagonal elements, and then you just this one time this one time this one. Okay, you get the result. But to be complicated, we just or here we can get the result. You know, this one just very easy. Just practice. You know, just practice. Okay, just practice, please. Okay, so here we have 2. We would like to modify. Hey, no, this is the other one. Yeah. Okay, sorry. Okay, so here we can get the determinants of this one, right? Okay, so you get determinant of A minus. Okay, I select this one. Okay, so you get minus 1 times. Okay, so we have we have of course, it's up to you. Okay, or you can take the diagonal elements, and we take the product. Yeah, you get the result also. Okay, or you have many ways. It's up to you. Okay, so here you can get A minus 0. Okay, so you get minus A. Okay, and similarly, we factorize 2. Okay, this is the first column. This is the second column. So this is C1, this is C2, and this is C3. So if we factorize, remember that means we have 1 over 2 C1 related to C1. So you get 1 here, 2 here, minus 1 here, and then determinant of A is what? A 1 over C determinant of B. And here we have 1 over 2, so 1 divided by 1 over 2, you times 2 here. So yes, okay, yeah. And then the others, okay. So then anyway, you can get the you can. So this is R1, this is R2, this is R3. So we can make R2 minus 2R1 plus R2 related to R2, and R1 plus R3 related to I3. Okay, you can, if we use this one, we can make sure, we sure determinant of A determinant of B, and then you get the result very quickly. Okay, similarly, so here, look, here we have minus 1, 2, 3, minus 6, and 5, minus 10. Okay, this is the special case. Why? Because if you times minus 2 with C1, and then, sorry, we times 2 with C1, and then with the plus C2, you relate to C2. So this one you get minus 2, 6, and 10. So you get the 0 column. So if we have a 0 column, we conclude that the determinant of A is 0. Okay, yeah. So anyways, it's up to you. We have many properties to apply for calculating the determinant. Okay, now we come back to the questions. I don't think I keep the on page 26, interchanging the 2 rows, leave behind a minus sign. May I ask why also should I write the factors of single row like that in the exams? I think it may be taken for factors for the whole matrix. Okay, yes, we can demonstrate. Okay, I mentioned before, this is the properties. Okay, this is the properties. So if this is the properties, you can demonstrate. You know, very easy to demonstrate, but I don't have more time. How can I say? Maybe I just give you some hint and you can understand for yourself, because I cannot demonstrate any theorem for you. Okay, so here we have I to J to K like physics 1, right? Okay, so then if we follow the sequence, okay, so we have I, J, K, okay, 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 I, J, K, okay Yes. Okay. So here you can get I. Okay. I cross I. Okay. I cross J. Okay. And then we have I cross K. This one line dimension, dimension. So if we have I cross J, you get K. So if we take J cross I, you get minus K. Okay. This one like the example to demonstrate why we interchange two rows. Determinant of A is minus determinant of B. Just give you some hints, okay, and then you can understand for yourself. Is it clear? What's your name? I see. Minh Khang, do you understand? Yeah, I give you some hint, okay, and you know why, right? Okay, yeah. So for yes, for, because this is the theorem. If we have theorem, we have properties. We need to demonstrate. Okay, so if you would like to demonstrate, okay, you can ask ChatGPT, you can read textbook, or you can apply the knowledge I give you. Okay, I instructed you. Okay, yeah, we don't have more time to demonstrate. Yeah, theorem by theorem. Okay, we don't have more times. Okay, please apologize. Okay, to you. Other questions so far? Okay, yeah, continue. We have one more question. Geometrically, is the determinant the errors of an image of one and one squares? I cannot understand clearly the meaning of your questions. You mean the image for what? Image for transformation or just the computer vision? Okay, just yeah, you should make clear. Okay, yeah. So again, if you study machine learning or computer vision or image processing, we apply many. I mean, after applying the transformations using that matrix. Let me think. Maybe correct. We need to demonstrate. We need to demonstrate the transformations matrix. Okay, so wait for the lecture 5. I will give you detailed answers. Okay, yeah. Okay, please remind me. We have lecture 5. We discuss very details about linear transformation. Okay. Okay, we're coming back. So continue. So here just some theorems. Okay, so if A is a square matrix and any one of the conditions below is true, that means the determinant is 0. Okay, we have an entire rows or entire columns. Okay, consists of 0. I mean we have 0 rows or column. two rows or columns are equal. One row or columns is a multiple of another rows or column. Okay, so if we can recognize some properties like this, okay, we can conclude directly determinants of the matrix is zero. Okay, yeah. Okay, so for example, here we have zero row. We have the same row 1 and row 3. Okay, so here we have C3 is minus 3 C1. Okay, yes, yeah. So here like this, we have one rows or columns is a multiple of another rows or column. Okay, and we have some examples. Okay, yeah. For example, we calculate determinant of A, right? How many? Yes. Okay. So we can see we need to modify, okay, R1, R2, R3, and then we we think about we use the third rule. I mean, we times C with R I plus Rj relate to Rj. So here we have minus 2 times R1 plus R2 relate to R2. So we have determinant of A, determinant of B, and you get here A1 for R1. This is 0 because we have minus 2. So minus A minus 2. Get here 0, you get here is minus 9. You have here is minus 2. And this is 0, 18, 4. Okay, and determinant. So you can see this is R1, R2, and R3. So we have R3 is minus 2 times R2. Okay, so we have the relationship between, I mean, the linear combination of R2 and R3. Okay, so from you get determinant is 0. Okay, yeah, yeah. Any questions so far? Maybe 1 minute for questions. If you have any questions, just let me know. Okay, I will answer to you directly, or okay, we need to wait for sometimes. Okay, some lectures we will understand more. Okay, so next, we have another example. Okay, so anyway, it's very easy, you know. For example, for this example, we recognize here we have 0. So we would like to modify 6 to become 0. Okay. So how can we do? So here we have here is C1, here is C2, here is C3, right? So if we consider if we consider 2 times C1 plus C3 relate to C3, relate to C3. Okay, you can modify this one to become 0. Yeah. So we can get what? We can get -3, 2, -3, 5, -4, 0. And then you times 2, so you get -6, 4, -6, -6 and -6 is 0, -3, this one is -4. Okay, so you can select this one. Okay, this is for here. So you get determinants of A is -3, right? -3 times C. For example, here the matrix B, B, C, cofactor C3, 1. Okay, this is of course you get what? You can get -3, and then you can get -15, -60. Is that correct? Oh, this is 4, this is 3, right? This is 3, 4 minus 1 is 3. You get 15s minus 16s. Okay, yeah, sorry, my mistake. Okay, so you can get 3. Okay, yeah, so determinant is 3. Sorry, 4 minus 1, you get 3, not -3, sorry. Okay, so anyway, yeah, you have more example, but this one is 5, 5, 5. Okay, yeah, a lot. Summary. Okay, if A is a square matrix, okay, if A, let A is a square matrix, if A has a row of 0 or column of 0, then determinant is 0. Okay, and determinant of A is equal to determinant of transpose of A. Okay, if A is the square matrix of the other n, and C is a scalar, then determinant of CA is yeah. Okay, so determinant of C times matrix A, okay, E C to the power of n determinant A. Okay, you know, C here is the common variables of the matrix, you know, of the matrix. So let's see. So, and then we have A with n rows and n column. Okay, so C is the common variables of all rows. So that means we have C times C, blah blah times C. We have NC. NC, that means C to the power of n. Determinants of A. Okay. Yeah, time determinants of A. Okay. And summary. Okay. So here, just review. You know, just review. So if we have scalar multiplication, okay. So if we have Ka1 blah blah, okay. So for determinants of this matrix E, K times determinants of this one. So if here we have one more K, you get here K square. If we have here K, you get K to the power of 3. Okay, so that means determinants of K times matrix A sorry, time here is matrix B, right? Time is matrix A. Okay, E k to the power of what? For example, A we have 3 row and 3 column. We have k to the power of 3. Determinant of A. Okay, yeah. Then this is for integers, and this one for the third rule. Okay, yeah. And then to theorem, if E result from multiplying a row of in by a non-zero number case, then determinant is k. That means we have identity matrix, and then we can get E by this rule. Okay, this is what I mean this one is scalar multiplication. Scalar multiplication. If we apply scalar multiplication to from I to get E, so determinant of E is k. Sorry, my laptop is too slow. Okay, let me. I need to delete some softwares. Maybe I will delete this one. I will delete this one. Okay, let me see. I don't know why it is. And maybe here I just close. Okay. Oh, any questions so far? Okay, so for no more questions, we continue. Okay, yeah. We hope it's better now. Okay, so if we have in and we would like to get we interchange. Sorry, too slow. Maybe I need to shelve it. Okay, then close and open again. Okay, so here we can get so if we apply the interchange, we can get determinant of E is -1. Okay, and if we add I mean the third rule, you get determinant of E is 1. Okay, just some theorems. Okay, it's very easy. For example, here we have identity matrix is 4 and 4, 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. Okay, yes. We get here, we times 3. Okay, we times 3 with R2 relate to R2. So determinants of A is 3. Okay, so we interchange R1 and R4. Okay, R1 and R4. You can get -1. Okay, and then if we apply the third rule, okay, determinant of elementary matrix. Okay, that is 1. Okay, very easy. I think that's enough. Okay, so we have some typical examples. Okay, you study for yourself. Yeah, now we have some exercise to help you practice. Okay, for example, determinant with properties of determinant of the equation. Okay, Yeah, for example, here we have okay, we can say we have R2E double R1. Okay, so determinant is 0. And yeah, so on. Okay, very easy. You just recognize. For example, here, why we get a 5 to the power of 3 or 6 to the power of 4, because if here, if we take 6 outside, you get 1 here, right? And then if you time 1 over 6, that means you take 6, you get 1 more 6. And here, over 6, 1 more 6. You time 1 over 6, you get 1 more 6, because we have, sorry. Yeah, because we know if we have C, Ri related to Ri, okay, we have determinant of A is 1 over C, determinant of B. Okay, so if we time 1 over 6, that means 1 over 6, you get 6. Okay, so if you do 4 times like this, you get 6 to the power of 4. Okay, and similarly for this one. Yeah. Okay, we find determinants, use elementary row or column operation to find the determinant. Okay, very easy. Okay, okay, verify determinants of A is E, the determinants of transpose of A. Okay, evaluate the determinants of the matrix by first reducing the matrix to row echelon form, and then use some combination of row operation and cofactor expansion. You can get determinant. Okay, yeah. For example, here for 11, you can think about we delete 1. Okay, we delete 2, delete 1, delete 2, delete 3. Sure. Okay, no, just here. That's okay. And then we have the upper triangular matrices. Yeah, well, if we have the format of upper triangular matrices, and then you take this one time, this one time, this one time, this one. Okay, we take the product of the diagonal elements. You can get the determinant of the matrix. Okay, so we finished session 2.2. Any questions so far? I don't know why is my computer is too slow. Okay, anyways, later on I will repeat. Okay, so continue. Now we go to section 2.3. We discuss about the properties of the determinants. Okay, more properties. For example, we have these properties. Look, we have determinants of A plus B will be different. The sum of determinants, individual determinant, right? Yeah. For example, here we have A, we have B. So determinant of A is 1, determinant of B is 8, and A plus B, you get determinant of A plus B is 23. Okay, so again, determinants of A plus B will be different from determinant of A plus determinant of B. Okay. Yes. Yeah, and we also already this property, right? Determinant of K times A is K to the power of N. k to the power of n, and we know A we have n row and n columns. Okay, so you get k to the power of n, determinant of A. Okay, so okay, here we have one more theorem. So determinant of C is equal to determinant of A plus determinant of B if and only if what? Look, let A, B, C to be square matrices. Okay, that differ only a single row. You know, differ only a single row. Say the row R, okay, or the row, okay, and assume that the R on the rows of C can be obtained by adding corresponding entries in the on the rows are on are on the rows of A and B, and then determinant of C is determinant of A not determinant of B. Okay, look, here we have A, here we have B. For A, we have A11, A12. For B, we have the same A11 and A12. Okay, yes. So when we calculate determinant, yeah, of A and determinant of B, we take the sum, you can get determinant of C. Okay, so here this is C. For example, do I have any examples? Yeah, this example. Okay. So for this example, this is A, right? This is matrix A, this is matrix B. So matrix A we have 175, 175. Okay, we have 203, 203. So we only have one row, a single row to be different. Okay, that means this one, this one like this one, and this one. Okay, we have the same R1 and R2. We have the different R3. Okay, R3. So we can apply these properties. Okay, we can get 175. Okay, we keep it. C, we keep it. So this is C. This is C. Okay, so matrix C, we just keep 175, 203. Just keep it, and then we have 1 plus 0. You get 1. 1 gets 0, you get 1, and 4 plus 1, and so on minus 1. Okay, just some properties. Okay, for your reference. So then this one is very important. Determinants of A times B is a determinant of A times determinant of B. Okay, this is interesting, right? Yeah. To determine determinants of A times B is a determinant of A times determinant of B. What is this? This one like L times U, LU factorization, right? LU factorization. So if we have determinant of U, determinants of U, determinant of U times determinants of L and of U, you can get determinant of I. Okay. We will discuss this one later. Okay. I remember we have maybe we have okay, just very easy, because we know what's the LU factorization, right? It's LU factorization. We have elementary matrices. Okay. Any questions so far? Okay, so continue. Yeah, we also discussed this one, right? Discuss this one. Just skip it. And we have grammar rules. Yeah, we will discuss about grammar rules. Yeah, very basic, you know. So if we have ix is b, okay. Look, we have ix is b, and we know A is the square matrix with n rows and n columns. Okay. So for example, for example, we have 3 and 3. So okay, so you get A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay? Yeah. And we have X. We have X1, X2, X3. And for B, we have B1, B2, B3. Okay? Yeah. So we have the grammar rules. Let A be an invertible and an N matrix. For any B in the real number set, the unique solution X of AX is B, a entries given by this ratio. So we have XIE determinant of AIB over determinant of A. Okay, so if we know A, we can get determinant of A, right? And then if we would like to calculate here x1, that means we have determinant of A1B over determinant of A. And what does this mean, A1B? A1B, that means we take the first column, okay, x1. So we take the first column out, and then you replace by B1, B2, B3. Okay, here, that means you can get determinant of A1B, and then we take this ratio, you can get x1. Okay, so if we want to calculate x2, so x2 is determinant of A2B over determinant of A. Okay, so when you just take the second column out and you replace by B1, B2, B3. Okay, yeah, and then you get determinant of A2B, you can get x2, and similarly you can get x3. Okay, now example. Now I will modify this one, so you can get A 3 minus 5 minus 2, 4. Okay, yeah. So we have two x, we have two elements x1 and x2. Okay, for B, we have B1 and B2. So if we would like to get x1 is determinant of A1B, y, right, over determinant of A. So determinant of A, how many? Determinant of A, you take this one times this one, you get 12 minus 10, you can get 2. So determinant of x1 is, okay, 2 here. So determinant of A1B, you take the first column out, and then you replace by matrix B, you get B1, B2, B1 is 6, B2 is 8, so you get 6, 8, right? And then minus 2, 4, you get determinant of A1B is 24 minus 16, then plus 16, you get 40 over 2, you get 20. Okay, you get 27 also. Okay, so this one we say grammar rules. Okay. We have the application of grammar rules. We talk about Laplace. Okay, Laplace. So for Laplace, we will study from electric circuit, right? Let me see, electric circuit or Laplace electric circuit or advanced mathematics, advanced math. Okay, it's covered by Professor Phạm Thanh Dương. Okay, this is the dean of our faculties. Okay, he will, Professor Young will teach you advanced math, talk about Laplace. Laplace is very important for electric circuit. Okay, try to study very well Laplace. Okay, Laplace. Okay, yeah, I will not teach you electric circuit. Okay, another lecturer will teach you. Okay, but I emphasize to you, Laplace is very important. Okay, for electric circuits, also for control engineering. Okay. So up to now, you can study for yourself what's a Laplace. Okay, you can use ChatGPT. Okay, or another AI platform. You can understand what's a Laplace. Okay, or you just type what's the application of Laplace. Okay, they will tell you. They will tell you. Okay, so a square matrix A is invertible. Invertible means non-singular if and only if determinant of A different from 0. Yes, of course, we discussed this one many times. Okay, so, or we can say A is invertible. A is invertible. What does it mean? A invertible doesn't mean we can figure out inverse of A, right? So this theorem is very important. If determinant is different from 0, you can find out inverse of A. Inverse of A. Okay, yeah, because 1 over A means inverse of A. Means inverse of A. So remember, you can find out the inverse of A if determinant of A is different from 0. Okay, yeah. So in the final exam, I remember I asked you to calculate determinant, and then I also asked you to whether we can find the inverse of A or not, and what is and why, and what is inverse of A. Okay, yeah. Okay, so this properties is also very important. Okay, why? Because we can calculate determinants of inverse of A very quickly by calculating the reciprocal of determinant of A. Okay, please remember this one. Please remember this one very carefully, because for the final exams, I give you A, and I ask you to calculate determinant of inverse of A. Many students calculate inverse of A, take a long time, because we need to modify AI become I inverse of A. After that, they calculate determinants of inverse of A. Okay, you take a long time. Okay, so you just calculate determinant of A, and then we take the reciprocal. We take the inversion of determinant of A, or reciprocal of determinant of A. You can get determinant of inverse of A very quickly. Okay, yeah. So that is the reason some student from the reverse in text, okay, complain to me why the final exam of linear algebra is too long. Actually, it's not too long, because you don't understand, you don't remember the properties. Okay, so when you get A, you try to get inverse of A, and then you calculate determinant, take more times. So to be careful, if I emphasize to you, try to remember, try to take some notes, and then you can add these notes into the cheat sheet. Okay, and you can remember, okay, for the final exams. Okay, or if you attend my lectures, I also emphasize the important things to you. Okay, no questions so far? Any questions? Today, are there any questions in the class? Hello, Jay. Any questions? Okay. So if no questions, we continue. So yeah, we have some properties. Okay, this one's very is very easy. You can understand for yourself. Okay, equivalent conditions for non-singular matrices. Okay, matrix. Sorry, a non-singular matrix always says invertible matrix. Okay, invertible matrix. So as is invertibles, determinants of A will be different from 0. We can get A can be written as the product of elementary matrices. Okay, AX is 0 has only trivial solution. AX is B has a unique solution for every n rows in one column matrix B. Okay, anyway, very easy. So from okay, so here we have another theorem. Yeah, so we can apply these properties to calculate inverse of A. Okay, we don't need to apply I inverse of A. No. Okay, if we know A, for example, A we have A11, A12, blah blah, A1n. Okay, blah blah, we have AN1, AN2, AN2, blah blah blah, and then ANN. Okay, so we can get cofactor, right? So A11 you get cofactor 1 1, blah blah blah, 1n, blah blah blah, n1, blah blah blah, 2, and n. So when we compare this one and this one, okay, so this one like, so if here I say here is cofactors matrix. So this one is cofactor matrix, this one is transpose of cofactor matrix, right? Because here you can see we have C11 to C1n, okay? But now this is C11 to C1n here. So this is the first row to becomes the first column. The second row become the second columns, and the last row to become the last columns. So if here we say this one is cofactors matrix, you can cofactors matrix or the matrix of cofactors. So this one is the transpose. This one is the transpose, right? This is the transpose. This is the transpose of. This is the transpose of. Okay, so here if we know C, you can take the transpose of C. Of course, C is the matrix of cofactors. Okay, we take the transpose of this matrix. Okay, the transpose of this matrix is called the adjoint of A. Adjoint of A. Okay, here the adjoint of A. Okay. The term adjoint also has another meaning is advantage on linear transformation. Okay, so we will study adjoint from machine learning. Okay, from machine learning, or you can ask ChatGPT. Okay, what is the application of adjoint? They will give you some ideas. But now I cannot cover everything in this course. Okay, so here if we know the transpose of C, okay, the transpose of C, you time 1 over determinant of A, you can guess inverse of A. Okay, I cannot say this method is better than this method. No, no. Just give you some ideas. We have another method to calculate inverse of A. Okay, yeah. Okay, so for example, here you can get a cofactor matrix. We take the transpose. Okay, and then we calculate determinant of A. Okay, yeah, determinant of A. And then you can guess inverse of the matrix. Okay, yeah. Of course, this one will not this one will not appear in the final exams. Okay, don't worry. So we also discuss about grammar rules, right? Okay, and we finished session 2.3, the properties of determinant, and then we have some exercise to practice. Okay, and we have the application of determinant. Okay, we also talk about a joint. Okay, yeah, we find a joint to find the inverse of the matrix. We already do that. Okay, grammar rules to solve a system of n linear equations, right? Remember we have xie, determinant of aib, right? Divided by determinant of a, right? This is grammar rules. Okay, and a joint, that means inverse of AE 1 over determinant of A and CT. Okay, CT. What does it mean, CT? CT is the transpose of, right? The transpose of cofactors matrix. Okay, and use determinant to find the errors of volumes and the equations of lines or blend. Okay, so this one come from the question from the students before, right? You determinant to find areas, volumes, and the equation of lines and blends. Okay, so we already know this one is cofactors, right? We can get a joint, and then you can get the inverse of the matrix. Okay, yeah, we studied before, right? Yeah. Inverse of A is 1 over determinant of A times a joint of the cofactors transpose. Okay, grammar rules we already know. Okay, and then we talk about use determinant to find the areas, the volumes, and the equation of lines or planes. Okay, so for example, we calculate the areas of the triangles in the xy plane. Okay, we have 3 point 1, point 2, point 3. Okay, yeah. So we have the formula determinant, the areas is plus or minus 1 over 2 determinant of x1, y1, 1, x2, y2, 1, and x3, y3, 1. Okay, it depends on plus or minus, it depends on the positive areas or negative area. Okay, so this is the first quadrant. It's the third quadrant, so the area is positive areas. Okay. Okay, and then when we calculate determinant, we divide this by 2, you can get the areas. Okay, and we calculate the trapezoid. Okay, so yeah. We have trapezoid 1, x1, x1, 0 here. Okay, x1, s1, y1, x3, and then x3, 0. Okay, you get this one. Okay, trapezoid 2. Trapezoid 2 will be, let me see, 830, 8330. I mean this one. And we have trapezoid 3 is x1, 0, x1, 1, x2, 2, and then, I mean, this one. Okay, so if you take these ones, okay, so we have the areas is, yeah, we have the trapezoid 1 plus trapezoid 2 minus trapezoid 3. Okay, so we can guess this one. Okay, that's mean the demonstration, the demonstration why we get in the areas here. Okay. Yeah. No. Okay, so what is it? This is the areas of trapezoid. Okay, trapezoid. So according to the linear equation of areas of the trapezoid, okay, we can demonstrate why the areas of the triangulars of the triangles in the xy planes will be calculated by this formula. Okay, and this is the explanation. Okay, just some example. Okay, so yeah, we will not go details. Okay, so just some applications. Okay. Okay, test for collinear points in the xy plane. Okay, and this is the application. We have collinear point. So when you study machine learning, we will study what is collinear point. Okay, so yes, for your reference. Okay, so we finished lecture 2. We have homework, I think. Yes, we have homework. Okay, homework 1. We evaluate the determinant of the given matrix, okay, by the cofactor expansion. Okay, you must use cofactor expansion, and then if we use elementary row operations to introduce zero in the matrix. Okay, so we have 2 ways. The first way, with your cofactors, we don't need to apply elementary row or column operation. Otherwise, we modify matrix A to become the simplified matrix by using elementary row operation, and then we take the determinant. Okay, so from what to verify, okay, determinant of A times determinant of B. This is not absolute, determinant. Determinant of A times determinant of B, determinant of A times B. Okay, verify these ones. Okay, determinant of transpose of A, determinant of A to the power of 3, transpose of A times A, blah, blah, blah. Okay, Riemann rules. Okay, solve linear equations. The system of linear equation by each of the methods listed below. Okay, when you go elimination with back substitution, Gauss-Jordan and elimination, and so on. Okay, so we just have homework 1 and homework 2, and please submit to me next times. Okay, yeah, of course you enjoy the New Year's, but don't forget to do the homework. Okay. Yeah, so we finished lecture 2. So any questions so far? Nice. So questions. Sure, I had a question. If we have the matrix A to the power of 3, is there any quick way to calculate determinants of or we have to multiply that and to line usual with coefficients expansions? So I think we just calculate let me think the easiest way first. Okay. I think we need to follow these the normal ways. Okay. Like coefficient expansion, that's okay. Okay, that's mean determinants of A to the power of 3 is determinant total, determinant to the power of 3. Okay, yeah, that's okay. Okay, so how about for Tungman, any questions? So for weekend, let me see. I think in a way we also calculate determinant of A, and then we take 3 times of determinants of A. Okay. Yeah, this is where we can use coefficient expansion. Yeah, that's okay. That's okay. Okay. Yeah. One more questions? Yeah, we just apply the properties. You can use coefficient expansion, or we calculate determinants of A to the power of 3. Okay. Other questions? Okay, so if no, we take break. Now, let me see. Okay. Now we have 2:36, and we will come back at 2:50. Okay, 2:50. Yeah, 10-minute break. Okay, see you later. And we will study Visit 3. Okay. Okay, we continue. Okay, so I hope you can hear me, TA. Anyone hear me? So maybe the microphone of TA's has problem. I cannot hear you. Okay. And then okay, that's okay. Um. Anyway, I hope you enjoy. I could too. Okay, and now we come to the new lectures, the new theory, and lecture three is also very important. Okay, for us. Yeah, I mean, many lectures I give you, okay, are all important. Okay, so I will share my screen to all of you, and now we enjoy lecture three. Okay, and again, if you cannot follow my lectures, don't worry. You can ask TA. You can ask me because I will come to the class. Okay, for New Year, you also watch the video. Okay, yeah, and we if your English is not good, okay, don't worry. When I upload the recording, we have I mean the subtitle. Okay, and then you can understand. Okay, yeah, and I hope many of you can pass this course. Okay, yeah, to get a good start, to get a good start for next semester. Okay, so for now we come to letter two. Okay, so let me check. Okay, so how about my screen? Yeah, okay. So lecture three, uh, we have three parts. Okay, lecture three part one, lecture three part two, and lecture three part three. So we need at least three classes to finish lecture three. Okay. So for now, in this afternoon, to we hope we can finish lecture three part one. Okay. So lecture three we discuss a lot of things. Okay, but for lecture three part one, we just focus on vectors in n dimension. Okay, Rn does mean we have real number and n dimension. N dimension. We have R2 2 dimension, R3 3 dimensions, and so on. Okay, yeah, R3. So when we mention about R2, does mean we imply xy coordinate R3 does mean xy z coordinate. Okay, yeah. We discuss about spaces and subspaces. Okay, so this is for lecture one, lecture three, part one. Okay, and this one for lecture three, part two, and this one for lecture three, part three. Okay, so yeah, part one we discuss about Euclidean vector spaces. Okay, Euclidean vector spaces. What's the meaning of vectors in two space, three space, and space? Norm. Okay, sometimes we say norm, sometimes we say length. Okay, dot product, distance in Rn, and cross product. Okay, very easy. So geometric vectors, engineers and physicists, okay, physicists represent vectors in 2 dimensions, we say 2 space, or 3 dimensions, okay, we say 3 space. Okay, yeah. Okay, and we have the vectors, we have the tail of the vectors and the tip of the vectors. Okay, for example, here we just review, we have vector v light vector ab. This is initial point, this is the terminal point or final point, so we have vector v or vector ab. Okay, so if we have y and x, okay, we have here we have point a, and we get a vector oa. Okay, oa, vector oa, because oa is 0 0 and a we have xa ya. Sometimes we say vector oa, sometimes we just say vector a. That's okay. It's because we have 0. Okay, yeah, so we say 0a, I mean oa or vector a. Okay, like this. Yeah, we know, right? So we have vector additions, we know. Yeah. Okay, we apply parallelograms rule, okay, to get the vector addition. Very easy. So just review, just review. We have vector v, we have vector w. You can get to apply parallelogram rules. You can get vector v plus vector w. Okay, vector v we can use one face, or you can use the vectors. Okay, vector v plus vector w. Okay. We have vector extractions, we know before, right? We have vector v w minus v. So we have vector v, we figure out for minus v, and then we take a w plus minus vector v. Okay, you can get these vectors. Or if here we have vector w with vector w is minus vector v, so we get the resultant vector c. So the tip will be here in the, sorry, the tail will be here and the tip will be here. Okay. The tail will be at the strand v, and this is for W. Okay. We have scalar multiplication, we know, right? Okay, and then yeah, we have the sum of 3 or more vectors. Very easy. Okay, we apply the associative law. For distance, you can get u plus totally v plus w is u plus v totally plus w. Okay, yeah, very easy. Okay, so finish. Now we discuss about this one. Okay, we have SMS before. Here we can say we have vector b1. Okay, or we say OP1. Here we have OP2. Okay, so if we take OP2 minus OP1, you can get B1, B2. Okay, B1, B2, these vectors. This vector. Okay. And we know B1, B2 is X2, right? Minus X1. And Y2 minus Y1. Okay, these vectors. So we have OB2 minus OB1, OB2, we have X2 minus 0 is X2, Y2 minus 0 is Y2, and OB1 is here. So these vectors minus the vector mean X2 minus X1 and Y2 minus Y1. So we have B1, B2 is OB2 minus OB1. Okay, just a very simple, just review, Yeah, so based on this review, you can see, for example, if I have any vector like this is a vector A, B, okay, vector A, B. So this is point 8, this is point B. So, and then if we have coordinates like this, okay, so we have the vector here is RA, and the vector here is RB. Okay, this is vector RA, this is vector RB. So we have vector AB is vector OB minus vector RA. Okay, so any vectors, if we have the coordinate, okay, that means you stay here. Okay, you can observe these vectors. Okay, yeah, that's one. So we have point B1 and we have point B2. We can get the coordinates of these vectors. Okay, so the coordinates or the components of vector B1, B2. E 2 minus 2 minus 7, you get minus 5. Sorry, 7 minus 2, you get 5. 5 minus 1, you get 6. And minus 8 minus 4, you get minus 12. Okay, very easy. Yeah, so now I hope you are familiar with vectors and how to represent the vectors in the coordinate. Okay, so now we have n dimension. We have Rn. Rn does mean we have this space with n dimension. So any vector v, we can indicate we have element v1, element v2, element v3, blah blah blah, to element vn. That means every vectors we have n dimension in n element, n components. Okay, yeah. So Rn. So if we have R3 and we would like to indicate vector v, okay, so vector v is to include v1, v2, and v3. Okay, because we have 3 dimensions, v1, v2, v3. So up to now, if I say vector v, vector y, vector z belong to R4, something like that, that means every vectors will have 4 elements, right? v1, v2, v3, v4, and of course all elements belong to real number set. Okay, and we have vector y is including y1, y2, y3, y4, and similarly we have vector z is including z1, z2, z3, and z4. Okay, yeah, now I hope you enjoy it. Okay, so yeah, now look, we have vectors v. How many dimensions? Now the operation on vector in Rn. So Rn, so we have n dimension. Well, vector w, we have n dimension also. Okay, and then we can practice. Okay, actually we can implement addition, subtraction, okay, multiplications, and so on. Okay, yeah. So now we have v plus w. This is addition, right? So we have v1, the element v1 plus the element w1, v2 plus w2, blah blah blah, vn plus wn. K times v, this is k scalar, non-zero scalar. We have kv1, kv2, blah blah, kvn, minus v, so you get minus v1, 1 up to blah blah blah. Okay, so yeah, anyway, this is the definition of operation on vectors is Rn. Okay, yeah, and we have some properties. Okay, you need to study for yourself, very easy. Okay, just about distance, associative law, multiplication, scalar multiplications, and blah blah blah. Okay, yeah. So now linear combination. Okay, we know linear combination, right? Okay, so this is the linear combination of vectors. You know, linear combination of vectors. Okay, so we have this space. How many vectors? We have a lot. Okay, we have this space Rn. So we have vector v, vector w, vector v1, right? Vector v2, vector v3, blah blah blah. We have many vectors in this space. Okay, so if we can indicate vector w e, the linear combination of the other vectors. Okay, so you get k1 v1 plus k2 v2 plus blah 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 plus kr vr. Okay, of course this one is vectors, and this one is coefficients. Okay, yeah, this one we say coefficient of linear combination. Okay, yeah, So here we say we have the linear combination of the vectors. How many dimension? N dimension. N dimension. Okay, so now I ask you the questions. So if we consider this one, can we indicate the linear equations, the linear system? Yes or no? The answer is yes. The answer is yes. Of course, the linear vectors, the linear combination of the vectors, but you can indicate like linear equation because for vector W, we have W1, W2, blah, 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 to Wn. For vector V1, we have V11, V12, blah, blah, V1, n. Okay, blah, blah, we have VR, we have VR1, VR2, blah, blah, VR, Rn. So now if we indicate the linear system, we have W1 E K1 times V1 1 plus K2 times V2 1 plus blah 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 plus KR times VR1 and then W2 E K1 V1 2, right? V12 plus K2 V22 plus blah 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 plus KR V2R. Okay, blah blah blah. Okay, so the linear combination of the vectors we can modify to get the linear systems. The linear systems. Okay, any questions so far? Well, easy, right? Okay. So if you attend my classes, okay, from lecture 1 up to now, you know, I believe that you understand what I am teaching. Okay. So for yeah, continue. So any vectors we have vector V, we have V1, V2, blah 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 2, Vn. We have an element of the vectors. Now we think about the matrix representation. We think about the matrix representation. So vector V, now I can indicate the column vectors. Is that okay? Is that possible? Yes. Okay. So now we have one column V1, V2, blah 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 2, Vn. Or if we have the vector V, can I indicate the row vectors? I mean V1, V2, blah blah 2, Vn. Yeah, this is row vectors, this is the column vector. So I say both of them are possible. Okay, you can indicate any vector to become the column vectors or become the row vector. That's okay. It depends on the situation. It depends on the mathematical expression. Okay, we can use column vector or row vector to express the row matrix or column matrix to express the vectors with n dimension. Okay, n dimension. Of course, this is space I. No questions so far? Maybe 1 minute for questions. Let me check any questions. So, no questions? Continue. I think lecture 3 part 1 is very easy. Okay, it's very understandable for all of students. Okay, so we have exercise, just practice. Okay, find the components of vectors. Okay, yeah. So we have boy A, right? We have 1, 5. Boy B, we have 4, 1. So you can get vector AB is 4 minus 1 is 3, and 1 minus 5 is minus 4. Oh my God, very easy, right? Yeah. Okay. And find the components of the vectors B1, B2. Okay, yeah, very easy. Then we have vector yield. Okay, so the question for you now, what is space? What is space? How many dimensions? 1, 2, 3, 4, 5. So we say U and V belong to R5. We have real number, right? All elements are real numbers. Not complex number. Complex number we have A plus JB. But now we have A. Okay. So this is real number, and we have 5 dimensions. 1, 2, 3, 4, 5. 5 dimensions. Okay. U and V belong to R5. How about this one? U, V, W. Okay. Belong to R4. Okay. Okay, find scalars C1, C2, C3 for which the equation is satisfied. Okay, yeah, very easy. It's good. So now we discuss about norm, dot products, and distance. So we have the definition of the norm. So first of all, we have Rn, right? We have Rn, and we have vector V with n element, V1, V2, blah blah Vn. Okay, so we can calculate norm, or we say the length, or we say the magnitude. Okay, so we need to distinguish between amplitude and magnitude. Very different, you know. Amplitude may be positive, may be negative. For example, we have the current IT is E5 sine omega t. This is amplitude because when you draw the curve, you can get like this. So this is phi is a minus phi. Okay, for the magnitude, that means we take the absolute of phi. This is was positive phi. Okay, anyway, so that is the reason here we can make sure norm, length, magnitude. Okay, and because the magnitude is positive, so the length is positive, or the norm is positive. This one is positive, right? Okay, so we say we use double. Okay, double and double, straight. Okay, double. Okay, double slash. Okay, straight slash. Okay, so here we can get square root of V1 square plus V2 square plus blah 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 plus Vn square, because we have n dimension. Okay, so we get the norm or the magnitude. Okay, similar to complex number, we calculate these absolute values, right? We calculate absolute value of x. Okay, like this. So examples, we have vector V, okay, with I3, in I3. So we can get the norm, or the length, or the magnitude, okay. This is the square root of 14, okay. Or we can calculate here, you know, this is R4, and we have the norm in the square root of 2 square, blah blah blah. Okay, very easy. So now you understand with the norm. Okay, what's the norm and how to calculate the norm of the vectors. Okay, Okay, so we have some theorem. The norm is positive. The norm is 0 if and only if vector v is a 0 vector. Okay, this is 0, not the 0 vector, not number, 0 vector. And we have k times v, the norm of k times v is a absolute value of k, right? Absolute value, okay, times the norm of v, times the norm of v. Okay, yeah. Now we talk about the unit vectors. The unit vectors. So of course we know what is the unit vector, right? The unit vector means the norm is 1. If the norm is 1, we say we have the unit vectors. So if we don't have the unit vector, we can modify non-unit vectors becomes the unit vectors. By this ratio, we take the vector v divided by the norm, you can get unit vector. So any non-unit vectors, we can get the unit vectors. It depends on this ratio. For example, here, this is v1. So when we calculate the norm of v1, you get what? 2 square is 4, 4 square is 16, 1 and 64. So you get how many? 65 plus 20, you get 85. Okay. Okay, so this is different from 1. So vector v is non-unit vectors. So if we would like to get the unit vector, we have vector u1 is follow the formula. Is vector v1 over divided by the length of v. So vector v1 means we have 2 minus 4, 1 and 8 divided by what? Square root of 85. So we have 2 over square root of 85 minus 4 over square root of 85, 1 over the square root of 85, and 8 over the square root of 85. Okay, so this is the unit vectors. Okay, yeah. So when we take the square, so the square of, when we take the norm, so you get 85 over 85, so you get 1. So as I said, okay, any non-unit vectors, we can use this ratio. We take the non-unit vector divided by its norm, you can get the unit vectors. Okay, like this. And the question so far. I think it's easy, so no questions. Okay. Yeah, good. Yeah, good. Okay, so we have examples. Okay, of course, this one is non-unit vectors. So we calculate the norm. You get 2 square plus minus squared. This is 4, 1. You can get 9. The square root of 9 is 3. Okay, so if we would like to get the unit vector, but the u is the v over the norm of v, you get 2 over what? 2 over 3, 2 over 3, and minus 1 over 3. Okay, now you can check. So now we have the norm of v is the square root of what? 2 over 3 square plus 2 over 3 square plus 1 over 3 square. You get what? 4 over 9, 4 over 9, and 1 over 9. This is 1, right? This is 1. Okay, so you get 9 over 9, you get 1. Okay, very easy. Now we talk about the standard unit vectors. Okay, standard. Now we already know unit vectors, so now we we study standard unit vectors. So of course, the standard unit vector, the length of the standard unit vector should be 1, the length of the norm. And for the elements, okay, only one element is 1, the other will be 0. For example, here we have R3, we have 3 dimension, x, y, z. Okay, so because we have 3 axes, so we have 3 standard unit vectors. For vector I, okay, vector I implies x-axis, so the first element become 1, the other will be 0. J units to represent y-axis. Okay, so the second one will be 1, the other will be 0. Now k to represent the z-axis, so this one is 1, the other will be 0. Okay, so like physics, okay, like physics 1, now we know what's a non-unit vectors, what's a unit vectors, and what's a standard, right, unit vectors. Okay, units and standard units, the length of them will be 1, but for standards the element is 1, the other will be 0. But for unit vectors we don't need. Okay, the unit vector we just make sure the length of it, the norm of it to be 1, that's enough. But for standard we need to consider element by element. Only one element is 1, the other element will be 0s. Okay, any questions so far? Oh, no questions. Okay, so we continue if we have no questions. Yeah. Okay. Oh, questions. No question, just yellow. Okay, sorry. So sorry. Okay, so for now, we okay, so we talk about the linear combination. The linear combination of standard unit vectors. Okay, linear combination of standard unit vectors. Oh, I recognize some questions. So okay, we talk about the linear combination of standard unit vectors. Okay, so sometimes we say this standard unit vector is I overhead, J is overhead, K overhead. Okay, or this is for physics 1. But for physics 1, but for linear algebras, we just say is I, J, K. Okay, so or sometimes we can use E1, E2, E3 plus E8. It depends on how many dimensions. So if we have E3, so we have 3 standard unit vectors. E1, E1, 0, 0. E2 will be 0, 1, 0, and E3 will be 0, 0, 1. Okay. So if we have Rn, we have E1 blah 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 to En. So E1 we have 1 0 blah 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 0, because this is the first dimension. E1 does mean the first dimension to be 1, the first dimension to be 1, and the others will be 0. And for E2 we have 0, and the second element, the second dimension of the second dimension will be 1, and the other will be 0. And for En, we have 0 blah 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 to 1. Okay. Yeah. The n dimension or the nth element will be 1. Okay, like this. Okay, we say standard unit vectors. Okay, for Rn, E1, E2, En. So if we have any vector v, we have any vector v, v1, v2, blah blah vn. Okay, in Rn we can express like this. This is the linear combination of standard unit vectors. Okay, so if we have vector v with n element v1, v2, blah blah vn, so we have the first element v1 time unit vector is 1. Okay, plus v2 time unit vector e2, blah 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 blah, plus vn time unit vectors en. Okay, yes. Why? Because if we have v1 with time e1, that means we have 1 0 blah 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 0, plus v2 0 1 blah 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 0, and then plus blah 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 plus vn, okay, 0 blah 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 1. Okay, so we can get here, you get the v1 plus the other 0, you can get the v1 and here v2 times 1, you get v2, right? And the other will be 0, so you get the v1 v2 blah blah blah, so vn, you know, the same. So we have any or every vectors v belonging to Rn, you can indicate the linear combination of standard unit vectors. Okay, like we have example. Okay, maybe here example. I will copy it, and I put here. Yes, okay. So we have vector v belong to R3 because we have vector v is a2 minus 3, 4. Okay, so because R3, so we have E1 is 1, 0, 0, A2 is 0, 1, 0, and A3 we have 0, 0, 1. Okay. Yes. So we have vector v become 2 times vector e1 plus minus, right? Minus 3 times vector e2, and then plus 4 times vector e3. Okay. Yeah. Or we can use ijk because normally for R3 we don't use e1, e2, e3. We use ijk. Okay. So here I just 2, 1, 0, 0, minus 3, 0, 1, 0, right? And plus 4, you get 0, 0, 1. So here you get 2, 0, 0. Here you get, first of all, I guess minus plus here, so you get 0, minus 3, 0, right? And then we lose 4, 4, 0. Okay? So now we have these vectors plus this vector plus this vector. You get what? 2 plus 0 plus 0 is 2. 0 plus minus 2, 0 is minus 3, 0, 0, 4. Okay, so you get 2 minus 3, 4. 2 minus 3, 4. And yes, any vectors we can indicate the linear combination of unit vectors. Okay, so now we have vector attributes E 7, 3, minus 4, 5. Okay, so we can get 7E1 plus 3E2 minus 4E3 plus 5E4. Okay. Yes, this is the linear combination. Of standard unit vectors. Okay. Vietnamese meaning sự kết hợp tuyến tính của những cái vector đơn vị tiêu chuẩn. Okay. Yeah. So for now, I hope you enjoy it. Okay. So continue. Yes. We talk about the distance. Okay, distance in Rn. Okay, Rn and dimension. So for here we have the definition. We have vector u with n dimension, u1, u2, blah blah blah, un, and we have vector v, v1, v2, blah blah, vn. Okay, in the n dimension. Okay, real number set with n dimensions. Okay, so we do not distance like this. Okay, so distance between vector u and vector v is the norm of u minus v. The norm of u minus v. Okay, the norm of vector u minus vector v. Okay, so we have vector u is u1, u2, blah blah blah, un. We have vector v is v1, v2, blah blah blah, vn. So vector u is minus vector v is what? A u1 minus v1, right? What else? u2 minus v2, blah blah blah, un minus vn. Okay, so the norm of vector u minus vector v is, so now we have vector u minus vector v, so it's very easy to take the norm, right? So we have u1 minus v1 square plus u2 minus v2 square okay, plus blah 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 plus un minus vn square. Day 2. Okay. Yes, any questions so far? Okay, no questions, so we continue. So now we have examples. We have vector u and vector v belong to R4 because every vector we have 4 dimensions. Okay, so we would like to calculate the distance between vector u and vector v. That means we take the norm of vector u minus vector v. Okay, and we take the norm of vector u and vector v. And you know, vector u minus vector v is 1. U minus V 1 minus 0 is 1. 3 minus 7 is minus 4. Minus 2 you get minus 4. 7 minus 2 you get 5. 1 minus 4 minus 4 5. Okay, so then we have vector U minus vector V. So after that you can take the square root. You can get 1 square plus 4 square plus 4 squares plus 5 square. You get how many? 16, 25, 1, 32. You get 47, 57, 58. So you get square root of 58. Okay, square root of 58. Okay, so this is the distance between vector U and vector V. Distance. Okay. So for dot product, of course we know for dot product. Okay. So U vector U dot vector V mean the norm of vector U times the norm of vector V and cosine theta. Theta is the phase angle between vector U and vector V. You know, if we have R2 or R3, it's easy for you to calculate to determine theta. But if we have Rn, you know, we have a lot of dimensions. So, yeah, not easy to calculate to determine theta. Okay, but normally for practical applications, we just focus on maybe 2 or 3 dimensional space. Okay, R3s I can say 3-dimensional space. 3-dimensional space. R3. Okay, so here it's R2, right? R2. So we know the theta from vector V to vector U. Okay, so the theta. So theta is higher than 0 and less than pi. Okay. Yeah, like the geometries. Okay, geometrical circle. This is cosine. This is sine. Okay, so this one is 0. This one is pi. Okay, like this. So maybe dot product is positive. Maybe dot product is negative. That's okay. It depends on the cosine theta. Norm of U is negative, positive. Norm of V is positive. It depends on the size of the product, the values of the product, the negative, positive value of the product, depending on cosine theta. Okay. Yeah. So for example here, we have R3. We have vector V. We have vector U. So vector V we have A, right? We have the norm of V is 8. The norm of U is 1. Okay, and the theta is 45 is 1 over square root of 2. So you get the dot product. Okay, dot product is the norm of U is 1. The norm of V is 2 square root of 2, and the cosine theta is 1 over square root of 2. You get 2. So as I mentioned before, it's not easy to determine the cosine theta. U dot V is the norm of U, the norm of V, and cosine theta. Not easy to determine the theta if we have more than 3 dimensions. So we think about another formula. Okay, now I demonstrate to you. So for example, here is vector U mean vector OB, vector V mean vector OQ, right? This is OB. and this one is OQ. Okay, yeah. So we would like to calculate dot product of U and V. So here, so dot product of U and V is the norm of U, the norm of V cosine theta. So here is the norm of U, the norm of V cosine theta. And if we apply the law of cosine, we know how to calculate the vector BQ. So vector BQ square, I mean the norm of vector BQ square is the norm of U square plus the norm of V square minus 2 magnitude of U, magnitude of V, and cosine theta. Okay, so yes, and what's the vector BQ? Vector BQ is vector U minus, sorry, vector V minus vector U. You get vector BQ, right? Yeah. We have vector BQ is vector V minus vector U. Okay? Yeah. So according to this one, we can get cosine theta, right? Yeah, cosine theta. Cosine, this is the norm, right? This is the norm of vector BQ. That means we have the norm of vector V minus vector U square. This is square, right? And vector BQ is U minus V. So V minus U. So here the norm of BQ square then mean the norm of V minus U square. Okay. Minus what? Minus with the U square minus. Okay, if I move this one to be here, you can guess here is minus, right? Because we move this one to be here and the Q to be here, you can get a right. This is plus. So norm okay, norm of U square plus norm of V square minus vector V minus vector U square. Okay, divided by what? Divided by 2, the norm of U and the norm of V. Okay, yeah. I mean, from this one, you can modify to get this one, right? Yeah. Look, we just divide this by 2, and this one you just times here, so you get the magnitude of U, magnitude of V cosine theta in this one divided by 2, or we get half. Okay, so and what is it? This one is U dot V, right? U dot V. So this one is U dot V. So now U dot V is half the norm square plus V square minus V minus use the norm of V minus U square. Okay, just copy here. Okay, yeah. So now we can calculate the dot products based on this one. Okay, so look, the norm of U square in this one, right? The norm square is the U1 square plus U tuple. Okay, and the norm of V is here. And if we take V minus U totally, the norm of V minus U square is V1 minus U1 square, V2 minus U2 square, V3 minus U3 square. Okay, and then we just replace into here, and into here, you can get this one. Okay, you can get this one. So now if we observe this one, you cannot see any cosine theta, right? Cosine theta. So this one is very convenient if we calculate dot product for many dimension. Okay, so u dot v is u1 v1 plus u2 v2 plus u2 v3, and then if we have more, just blah blah blah, just plus un vn. Okay, yeah, and here you can get the dot products of two-dimensional space. So u dot v for R2 is u1 v1 plus u2 v2. That's all. Okay, so now if we extend with the u and with the v for Rn, we have dot product. We have dot products of u and v, e u1 times v1, u2 times v2 plus blah blah plus un times vn. Okay, so anyway, if we apply the physics one, okay, you can calculate u dot v, e, the norm of u, the norm of v, and cosine theta. Theta is the phase, theta is the phase angle of vector u and vector v. Okay, but if we consider linear algebras for Rn, we can calculate dot product in u1 times v1 plus u2 times v2 plus blah blah plus un times vn. Okay, and then we have some properties of the dot product. U dot v is v dot u, u dot v plus w is u dot v plus u plus w. Okay, the triple law. Vector 0 times vector v is equal to vector v times vector 0 equal to 0. Okay, here u dot v minus u dot w. Okay, and so on. Okay, so now this one for your reference, we have the properties, algebraic properties of the dot product. Okay, yeah, and this one for Cauchy-Schwarz inequality, just for your reference. Okay, so we have the absolute values of u dot v is less than absolute, because dot products may be positive or negative, so we have absolute values. So absolute values of u dot v is less than or equal to the length of u and the length of v. Just Cauchy-Schwarz inequality. Okay. Yeah. So the magnitude of u dot v is here. Okay, u1 times v1 plus u2 times v2 plus un. Okay, less than or equal to the norm of u. We take the square root, or we have the power of 1/2, and we have this here. Okay, to the to the power of 1/2. Okay, this is Cauchy's inequality. Okay. Some properties just for your reference. Okay, yeah, here the norm of u plus vector u plus vector v is less than or equal to the norm of u plus the norm of v. You can demonstrate for yourself, or we have the distance. The distance between vector u and vector v less than the distance of vector u and vector w plus vector w distance of w and v. Okay, yeah. Many properties, okay, or theorems. Okay, yeah. We have the norm of u plus v square plus the norm of u minus v square. Okay, E is equal to 2, the norm of u square plus the norm of v square. Okay, yeah. So this properties is also important. Okay, please remember it. Okay, so what time is it? Any questions so far? Okay, so if you have no question, let me check. Okay, so we cannot finish lecture 3 part 1 today, but just 2 more slides and then we can stop. Okay, so now we talk about u.v. Okay, u.v. So u.v, okay, it will be equal to the transpose of u times v or the transpose of v times u. Why? Because vector u here, this is the column. Okay, this is a column. That means we have 2 rows, 1 column. And vector v here, we have 3 rows and 1 column. So if we have u dot v equal to u 3 and 1, v 3 and 1, you cannot implement the matrix multiplication. So we need to take the transpose of v. So if we take the transpose of v, we have 1 rows and 3 column times v, 3 rows and 1 column, 3 and 3. So yeah, you can implement. Okay, to just symbol. Okay, so if we indicate u and v are column vectors, are on column vectors, we need to, when we take the dot product u dot v, we need to take the transpose of u times v or the transpose of v times u. Now we also have the dot product u dot v, but u is row vectors. Okay, and v is column vectors. Okay, so when we take u dot v, okay, equal to u times v, because for u we have 1 row 3 column, for v we have 3 rows 1 column, 3 and 3, you get u dot v. Okay, or if we take the transpose, we need to take the transpose on, okay, the transpose of v times transpose of u. Okay, so the transpose of okay, so u times v totally transpose, right? U times v totally transpose e, the transpose of v times the transpose of u. U dot v transpose. That means the transpose of v, the transpose of v times the transpose of u. Okay. Okay, all right. And then, yeah, I mean, it depends on the format of u and v. The format, if they are on columns, on column vectors, we need to follow this one. If one of them is columns vectors and the other one is row vectors, we need to take the u dot v or the transpose of them. Okay, or again, this one similar, you know, now u is row vector, v is column, now u is column and v is row vectors. Okay, or here the same, you know, all of them are row vectors. So it depends on your definition. Okay, normally I suggest you to use u and v are on column vector, on column vector, or u and v are on row vectors. Okay, just use. Okay, but of course you can use any format you want. Okay, yeah, u and v are on column vectors, u and v are on row vectors, or u is row, v is columns, or u is row and v is yeah, it's vice versa. It depends on you. Okay, so and then we can take the dot products. Okay, dot product. Okay, so I think we stop here, and after after New Year's, after New Year's, okay, see you in 2026. Okay, yeah, and enjoy your New Year holidays. Don't forget to do the homework. Okay, and see you New Year's. Happy New Year's to all. Okay, enjoy your holiday with your families. Okay, yeah. And now this is the time for TA. So now for TA will yeah, thank you so much, Mr. Yaki. Maybe I need to yeah, change the flight tickets and I will come back for my hometown area. Okay, so anyway, so here we now the time for TA 4. to for 15th. Okay. Yeah. Now the time for tonight. Okay. Support students. Okay. Yeah. Thank you so much. Bye bye.